Okay, so we're 3 minutes over. I like the number 3. It's a lucky number, so I say we go for it. Welcome everyone to the first Athena Science webinar of the new year 2024. Hope everybody had a great transition into the new year. And I'm very happy to introduce our speaker today is Angie Veronica, who is a PhD candidate within the dark energy team at the University of Bonn. And before that, she got her bachelor's degree in physics at the University of Leipzig. And after that, she got her master's degree also at the University of Bonn. So clearly she likes it there and decided to continue and stay on the team. Her master's thesis consisted of analyzing the interacting galaxy cluster system Abell 3391-3395. And I believe this is going to be also the topic of her presentation today. I'm sure that many people online today have not missed the wonderful eROSITA paper splash that happened on Archive also today. This was not part of that paper splash, but I think she will still talk about some beautiful eROSITA data. So in that sense, it's a very timely presentation. So Angie, thank you so much for joining us, and the floor is all yours.
Yeah. Thank you, Aurora, for a really amazing introduction, very detailed. Yes, I like Bonn, and I hope you can visit Bonn at some point. Yeah, so in today's talk, I will be talking about this project, still about the Abell 3391 and 95 system. But this is this is now my PhD project, and where I'm characterizing the warm-hot filaments that are detected in the system with eROSITA performance verification data. And in fact, the paper has just been out around last week, and so it's timely also for the talk. And of course, this project will not be out there without the help of my supervisors and also the eROSITA collaborators here that I listed on this paper here. And I would also like to thank Jacopo Bartaluzzi, Fabio Gastaldello, and also the collaborators from ENAF that has allowed me to share the prospect of studying the filaments with new Athena WFI that I will show you and share with you later in the talk. So let's start with a brief introduction. I believe everyone knows galaxy clusters. So they are the largest sphere-realized object in the universe. And in this beautiful image from Illustris simulator, we see a patch of a cosmic web filament, and galaxy cluster sits in the node of this cosmic web. And the galaxy clusters, they are connected by cosmic web filament. And this filament can be traced to trails of galaxies, as we can also see from this image. And galaxy cluster, over the time, they form and grow through accretion of matter, merging with other structures. And also these accretion and mergers of small structures are supplied by the filaments. So it's very interesting to study the outskirt and also the filaments, of course, and because there are so many phenomena involving accretion in this junction between the cluster and also between the filaments. And another thing that is of interest to study the filaments is this big question of the missing baryons, where we've seen also a lot of this pie chart from Nicastro 2017 that about 30 to 40% of the total baryons in the local universe are still missing, so to say, or unaccounted or not yet observed. And the solution is to look at them in the cosmic filaments, and they're supposedly located in the so-called Warm-Hot Intergalactic Medium, or WHIM for short. But it's pretty hard to detect them because of their properties, such that they have very faint density and also very soft temperature, and here typically can be observed in the soft X-ray. And so we need a sensitive instrument in the soft X-ray band, but also we can locate them by strategizing, that is to try to see the densest part of these cosmic web filaments, which is the outskirts of a nearby galaxy clusters or between a binary cluster system, for instance. And the efforts has been done numerous times with different X-ray telescopes. For instance, we have an example from Akamatsu 2018 here, where the authors study the Abell 401 and Abell 399, especially the region in between, to detect the filaments using several maximum Newton pointings. Also, there is a study of Abell 98 by Sarkar 2022 by Chandra, using Chandra pointings. And then here there is an example of study of galaxy cluster system Abell 7050 by Bulbul 2016, where we can see there are 3 components here. But as you can see here, it requires several pointings to observe outskirts of galaxy clusters, especially the nearby one. So therefore, we need an instrument that's sensitive and also have a wide field of view. And eROSITA is perfect for this because the field of view itself is already 1 degree diameter, and it's also now scanning the sky. eROSITA, it's launched in July 2019, and the goal is to discover 100,000 galaxy cluster so that we can constrain the nature of dark energy. And on top of that, it has also the goal to map the hot filamentary gas between galaxy cluster to map the exact large-scale structure in the universe. And this is, an excellent instrument to study the filaments. And another thing, therefore, during the performance verification, eROSITA do for observation of this galaxy cluster system, which is Abell 3391 and 95, that is located in the redshift of 0.05 and consists of several components. As we can see here in the ROSAT-OSKY survey image, we see the emission from Abell 3391 in the north, and then Abell 3395 here, that consists of 2 components, that is north and south. And here there is a famous galaxy group, which here probably it's really hard to see. And probably it's not resolved here in the ROSAT image. This galaxy group is famous, and there is a study of in detail using Chandra that this galaxy group are currently trying to pass by the bridge or the emission between these 2 clusters, and there is trail of ram pressure stripping, and it's very in general this is a very complex system. And as I mentioned, there is a Chandra observation that cover this field as well. It requires 5 pointings here to cover the Abell 3391, 95, and then the bridge region in between them. And that's exactly the ESO 161 galaxy group. And we also have maximum Newton pointings. There are 3 trying to cover here R500 of the cluster, and here both of the components we can see nicely. And in October 2019, we have the eROSITA performance verification of the field. So combining all 4 data, we cover 15 square degree of this field. And in fact, it cover up to 3 times R200 of the Abell 3391 cluster, which is marked here with the line circle. And in the paper of Ripley 2021, we discover a really amazing discovery that in fact there is emission beyond this 2 big cluster here that continuously it is 15 megaparsec long, and we dubbed it as northern filament, southern filament, and also towards the east of the Abell 3391 there is a potential eastern filament as well. And in total, it connects, at least in this field of view, we know it connects 5 galaxy groups and cluster. That is the northern clump here. And then the 2 big cluster here, the ESO 161 group. And there is a MCXC cluster outside the field of view, and we can see probably, I don't remember if it is the emission from R500 or R200 of that cluster at the edge of the field of view here. And we also have resolved this little clump that I will also discuss later. And upon the PV observation from eROSITA, we are also granted the pointing observation from XMM and Chandra that were performed almost simultaneously of this galaxy cluster here. We call it northern clump because it's in the north of the field of view. It has really unique morphology, as we see here from the XMM image, that we see that it's not spherical or elliptical, but it's boxy in shape. And also we see a trail of emission that looks like a tail pointing away from the main system. And we speculate this is the result of ram pressure stripping as it moves toward the south. We also have the ASCAP EMU data, and here we have a composite image beautifully done by our collaborator from Australia, Barbel Koribalski. The blue, we have the XMM Newton. We have also here a wide angle tail that's hosted by the BCG. This is shown in pink, and the ECAM optical map in green. And this filament is also confirmed in optical image, as we have seen here, the DECAM galaxy density. We see that there is a trail of overdensity that map and trace our filament here. So it's exciting, and we have seen the filament in X-ray and also in optical. And furthermore, we also have a paper by Marcus Bruggen, 2021, that described nicely all the radio sources in this Abel 3391 and 95 field. Now, the goal of this project that I'm doing is to characterize the detected filaments in Abel 3391 and 95 using the eROSITA PV data. So we are going to do we did the surface brightness analysis from the central of the cluster outwards. So we construct detailed surface brightness profiles in various directions, and also compare it with the sky background and compare it each other with the other sectors of and on filament. Also, we try to get the temperature of the cluster outskirts, which we define as the region between R500 and R200, and also the temperature of the filaments itself, that is the emission beyond the R200. And we try to also constrain the metallicities of the outskirts and also the filaments, and then also the gas electron density, then compare it with the predicted WHIM properties of the filaments from simulations. Now, coming to the first part, which is the surface brightness analysis, since we have 2 big clusters and the filaments that parents the filaments in different direction. For instance, the Abel 3391 parents the northern filament and eastern filament, and the southern filament is parented by the Abel 3395. So we have 2 separate profiles being constructed. First, here we have the one from Abel 3391. Essentially, we have one profile that goes from Abel 3391 through northern filament and then northern clump, and then eastern of the Abel 3391, and then going to the potential eastern filament, and then west and east as a sector that that are not connected by any filaments. Here it's a bit tricky because the components of Abel 3395 are are interacting with each other. So we try to have less impact from one of the component. Here we choose to focus on building profile of Able 3395 South and try to include the emission from the southern filament here by taking the half a circle and divide it into 5 same size sector, and suppose southern filament included in the sector 1 and 2, and then the other sector just to see how it compares to the other sectors. Now coming to the result of the first surface brightness profile. So it's a bit of a busy profile, but I would like to point you to the blue data points, and which is relevant for northern filament, and the red one that relevant for the eastern filament. From the core to R500, what's very apparent is that the profile for the north is lower than the other, while the orange is, or in the east, is a bit higher. So it just shows how Able 3391 is not completely spherical, but as we saw from the image, it's elliptical. So the blue one here means going to the north, means that the semi-minor is towards the north, and the semi-major of the elongation of the cluster is going east and westward. And above the R200, so in the filament region, we see above 3 sigma detection for the northern and eastern filament, while the eastern and western sector, they are all below 2 sigma. And for the southern filament profile, so from the core part of the profile is a bit interesting. There's so many variation, but what we see here, the red and the blue, which again corresponds or in the direction of the filament, they are a bit lower than the other, while sector 5 is higher than the other, and that's also can be seen from the image. We see that this component is not exactly peaked in the center of the bright or the core region, but towards the south. So in the sector 1 and 2, it ended or it gets lower very fast, while for the sector 5, it's much brighter there. As for the filament emission here, we see a really nice peak here that comes from this spatially resolved little clump. We dubbed it as little southern clump because it's in the south. And we see that in comparison to the sky background, which is the pink or magenta shaded area here, that the sector 1 and sector 2 are way above than the other. It's above the other sectors, which is sector 3, 4, and 5, that agree more with the sky background level of emission. Now, what about the temperature and also metallicity and density of this region? So we needed to do a spectral analysis. So here we only focus on the outskirts region of filament facing area of the cluster. So we have 2 for Able 3391, and then we have 1 from northern clump, and then 1 from Able 3395. So we have 2 different sky background region because the NH across the field of view is varying. So we try to get the area where the NH or the hydrogen density is of the same order with the source region. So for the north and east area, we use this sky background region, while for the south, we use this sky background region. Now for the first result, which is the temperature profile, we have one from the north here. So we have 4 data points. from the outskirt of the clusters, and here is the filament. So the two boxes act as one. So we do a joint analysis, or we combine the spectra of these two boxes essentially. We compare our data points with a universal temperature profile from galaxy cluster outskirts review by Ripridge 2013, and it supposedly described very well the temperature profiles of relaxed cluster from 0.3 to R200 of the cluster. And we see here that the data points or the temperature of the outskirt in this filament facing region of the cluster here are hotter than expected. And for the filament, the temperature of both this filament, northern and southern filament, is 1 kilo-electron-volt. So it is also hotter than predicted in the simulation. And also the metallicity is low. We have hard time constraining the metallicity. In fact, here for the northern filament, we estimated the metallicity to be lower than 0.01 solar, and here a metallicity of about 0.1 solar is estimated. And as for the outskirt metallicity, we have a range of 0.01 to 0.1 solar metallicity for northern clump, and then upper limit of 0.3 for the Abell 3391, and a huge range of metallicity for the Abell 3391, which is 0.4 to 1.2 solar metallicity. And another thing that we have resolved clump here, and we did an analysis to estimate the characteristic properties of the clump here. So we try to get the temperature, radius, and also and get the mass. And we have a mass of 2.3 times 10 to the power 13 solar mass, which is in agreement to a low mass galaxy group. And with that, we can do another analysis for southern filament, where we remove the emission from this little clump here. So the result is that the temperature of the filament doesn't change with or without this little galaxy group. However, the density decreases when by 30% when we remove this little galaxy group. So this shows how it is important to resolve and also identify galaxy group or clumps that reside in filament, as has been shown before. Also here I show how the contribution of the subhalos in the simulated filaments in illustrious TNG by Galarraga Espinosa 2021. So without the subhalos, the pressure goes down. So yeah, I think we have, it's very important to identify this clumping in the clumping bias, so to say, when studying the outskirt and also the filaments. Now, for the density itself, here there is a 2D phase space of baryon temperature against the baryon over density from Schul 2012, where we have different phase of gas. We have the warm-hot or WHIM, and we have the hot here, that more of an ICM region there. And if we plot roughly our result or the filaments in this system, those are between 98 and 238 and located here really close to the upper limit of the WHIM. In fact, the density is WHIM density, but the temperature is slightly higher. So we have a Q&A question. So I think I can just move on and read it later, I guess. So for here, before I move on to another part of the talk, I would like to summarize what we have found and what we have done in this project. That is that we have construct a really detailed surface brightness profile, goes beyond R200 and in different sectors as well. And we compare it with the sky background and also compare it with each other. Then we have identified and the temperature of the outskirts and also the filaments. So our results show that the outskirts of the clusters is hotter than predicted. And also our filaments is hotter, that is around 1 keV. But this is really close to the upper limit of the WHIM temperature from simulation, which is 0.9 keV. And another fact is that our filaments are short. These are only 2 to 3 megaparsec long filament, if we assume it to be lying on the plane of the sky. And also it is located in a dense region. We saw that many galaxy clusters and there are many components, including groups. So supposedly these filaments have been gravitationally heated and could be this due to this the temperature is boosted up. For the metallicity in the outskirt, the metallicity seems to be low, but it is still within the uncertainties of other studies. For instance, studies from Aurora here, studying the outskirt of Perseus, and there's another study of the outskirt of Ezer, another Abel cluster by Ezer in 2017, and another 10 nearby galaxy cluster by Urban in 2017, and it's still within also the predicted metallicity in simulation. For instance, here, magneticum simulation by Biffy in 2018. It's the same with the filament metallicity. Now for gas electron density, the filament density, in fact, is still within the range of the predicted filament or WHIM from simulation. And we also showed already that removing clumps had decreased the density by 30% by 30% in our analysis. Now this very interesting, so a little advertisement, but we are on the topic of filaments. There is another very interesting filament, an interesting result using eROS4, that is combining 4 eROSITA survey. This is a work done by our master student in Bonn here, but so Jakob Dietl has analyzed in very meticulous way the filament between Abel 3667 and 365 that's located at 0.05. So he predicted that the filament is longer than 30 megaparsec long. And he had done a very nice surface brightness profile here to confirm the significance, and the result is that the significance of this filament is above 11 sigma, and he also confirmed the filament with the 2-mass contour. So it's in other ways the galaxy over density. So yeah, that's also an advertisement for the eROSITA that are released today. So go for it. So this paper from Jakob is already out, and also the eROS extra catalog is out. So yeah, have a feast, I guess. And now let's go to the last part of the talk, which is it's a current ongoing work by Bartolucci and Gastaldello and collaborator from ENAF, where they are trying to see the prospect of studying filaments with new Athena WFI. So firstly, this is the simulation data set. They took 5 galaxy clusters from simulation, that is the 300 simulations by Chui et al. 2018. These 5 galaxy clusters are chosen to be the best object, the best candidate to study the filaments. They have the mass range between 15 to 25 10 to the power 14 solar mass, and they are extracted at redshift of 0.068. And for each of the cluster, there is information of emission measure that we can relate to the density and also temperature, which we can see here one example of the galaxy cluster that they use. Here, the R500, and also the filamentary structures at the edge of this of the cluster. Here is the temperature. So the strategy that they have developed for this identification is to have a longer pointing for the filament area, and then longer pointing away from the cluster for background observation. So for instance, in this example, they have done 100 kilosecond pointing in this filament here, and then 50 kilosecond in the other direction to constrain the sky background. And for the simulation, they have assumed the worst case setting among the current technical scenarios, and simulated with 60, and in order to get the WFI, in order to get the evenlies, so that they can extract surface brightness profile and study the output. So the WFI simulation results here, for instance, in this example, they have the 100 kilosecond filament pointing in this filament 1 and filament 2, and the background here. They constructed surface brightness profile of these two filaments and compare it with the background. And with this technique, they have detect above 3 sigma of this filament beyond the R500. And they also managed to, on top of the significance detection, they also managed to resolve clumps in the faint area, which is beyond the R500 of the cluster. And the end result is that using this technique and the worst configuration of the WFI, they were able to identify 6 out of 7 visible, out of the 7 filaments visible in simulation maps. So it's very exciting, and it's a really very hopeful and optimistic result for us studying filaments with the upcoming new Athena. So now I would like to conclude the talk. I hope I'm not over time. So here I showed the result of characterization of filament using eROSITA PV data in this specific galaxy cluster system. And also another study with the eROSITA data is currently being produced, and some are already out. And in the future, there will be more of these filaments being detected and studied. And of course, with new Athena, we'll also be able to do that. And but the bottom line for now, we are sure that the filaments are there as predicted by simulation. So this is amazing. And so we have characterized the filament properties, but we had still have a hard time constraining a robust metallicity measurement. So with new Athena, we can do that. But and this is a feat that can only done. It cannot be done by other means like ASI stacking. And also XIFU can measure filament through absorption, but WFI with the wide field of view can give a complete overview of the spatial distribution of the filament. And considered the worst technical setting even, that in Bartolucci, in preparation, we managed to detect above 3 sigma level detection. Another thing is that resolving and identifying the clumps and groups. So we show how important it is to identify this clumping or the bias from the clumping to not overestimate. And I think this is going to be a feat that Athena will be able to do when it's there. So yeah, thank you very much. Question and feedback are welcome. Thank you.
Great. Thank you, Angie. That was a really, really fantastic talk. Thank you so much for this. I think you really hit the right balance between exciting new results, but also showing what that means for the future, you know, extrapolating these new discoveries that we are just getting right now into the new Athena era. And I think this is exactly what we want to achieve with these science webinars. So that was really excellent. Thank you so much for that. To the audience, I think please raise your hand and we will allow you to unmute if you have a question, or you can type it into the Q&A and I can read it out if you prefer that way. We already have two questions actually in the Q&A. The first one was from Florent, who asks, what method have you used to estimate the M500 of the Little Southern Clump to be around, he says 2.33 solar mass, but I think there is a 10 to the something missing there.
Yes.
But how did you estimate M500?
Yeah, so the mass is 2.3 times 10 to the power 13 solar mass, so it's a little galaxy group. So what here we estimated through scaling relation, which is between the temperature and mass. So from the temperature we can get the M500, and from the M500 we can get the R500. So I hope that answered the question.
Yes, okay. So in fact, you use only the temperature and not the density.
Yes, exactly.
Okay, thank you very much. And very good talk, by the way.
Thank you.
Okay, then the next I saw is from Anwesh Mayunder. Anwesh, you were allowed to speak. Would you like to ask your question or should I read it? He's still muted, so I will read the question. Anwesh wants to know how low the densities of the filaments can be for eROSITA to be able to detect. So in other words, what are the lowest filament densities that you would be sensitive with eROSITA? He says, I understand that ultimately depends on how well you can measure the CXB, but I want to get an idea about what kind of density that translates to.
Mm-hmm. Yeah, so these filaments are in the order, can I, maybe do I have it? Maybe I don't. So I think if I remember correctly, it's in the order of 10 to the power minus 6 per cubic centimeter. Let me dig up the very quickly. Oh. Mm-hmm. Yes. Yeah, sorry. So yeah, it's in the order of 10 to the power minus 5 per cubic centimeter. So as of the I'm not exactly certain on what's the lowest density we can detect, but obviously we need the X-ray emission from the cluster itself. So sorry, from the filaments itself. So it should be, at least if you check from the image, you would need maybe above 3 sigma level detection from above the sky background, I would say.
These I assume these values are included in your latest paper on, at least for this particular system of galaxy clusters and filaments.
Yes, it is in the table. So yeah, it should be there. Yes.
I have a question, and I'm going to jump in front of Matteo. I'm sorry, and then I will give the mic to Matteo, who has his hand raised. I'm wondering if these, building upon what Anwesh was asking, these densities, I'm wondering if some of these filaments discovered by eROSITA are even denser than maybe what we are finding right now in simulations, because I remember this work with Jacopo Bartolucci. It's possible to detect filaments with New Athena, but I think given how, I don't want to say easy, but easy it was to find a couple of these with eROSITA, I think maybe it might be even easier than we think based on the simulations, that there might be examples of quite dense filaments that it may be even easier to see with New Athena than the simulations currently tell us. Am I too optimistic? I mean, I tend to be too optimistic. Am I too optimistic? What is your feeling about this?
I would say I would agree with your optimism. So for instance, here Jakob used 4 of the eras data, which maybe it's amount to 800 second of exposure. And this filament, it's surprisingly also hotter than we thought. So for instance, here, the fact that we can see it should be also around 1 kV. So I think with Athena, we can easily see the filaments that currently being detected in eROSITA, and maybe we can even go further in search of these filaments with new Athena.
Okay, I won't belabor any longer. Matteo, would you like to ask your question?
Yeah, thank you, Aurora. Thank you, Angie. Excellent talk. Amazing results, really exciting stuff. I have to admit that the comment by Aurora would leave me to ask if the optimism has an implication on the detectability of this filament with X-IFU, but that's not my question today. My question for Angie is on the low level of metallicity that you detect in these filaments. Now, a thermal plasma, bear with me for the naive question, but the thermal plasma with a 1 kV temperature and metallicity lower than 0.1 solar will resemble very closely a featureless spectrum. So my question is how actually these results, to what extent these results is robust against the possible systematic effects like dilution from not perfectly subtracted point-like sources or estimation of the various components of the background that may have a systematic impact on these low metallicity measurements.
Mm-hmm. Yeah. So especially the northern filament, that it has really low metallicity, that we can only detect the upper limits. But if we compare to simulation, for instance, the magneticum simulation, this is still within the predicted value, although it's very low. But for systematic checks, we have tried to also come up with some tests to see that what we are showing in the main table is robust. So, for instance, we have treated the filament as a foreground component, for instance, like just in case maybe this is not a filament, but we are seeing a foreground emission. So we have tried to fit the outskirt region of the cluster and using the filament as a what is it called as sky background, but the result is really unphysical, so to say. And there are other couple tests that is included in the paper, and I think the bottom line with all these tests, we conclude that the result is, I think the filaments is there, but obviously there is something that we need to improve with the metallicity measurement. So thank you for the question. I hope that kind of answer the question or the doubt.
Yeah, thank you. Very clear. Thanks again for the talk.
And I think I will disappoint many members of this audience if I didn't follow that up with the question of how robust this metallicity is to any multi-phase of the gas. We expect the gas to have maybe a distribution of temperatures. And at 1 kV, the metallicity comes from the iron L bump that has been notorious at biasing metallicities. So are we sure that the metallicity is not higher, but the gas has a different temperature structure than assumed?
Mm-hmm. Yeah, so we have also done the 2 temperature fitting, which we have this 2 temperature fitting. We actually, one of the temperature is higher, so 1 kV, 1.2 kV, still around the temperature we obtained for the cluster, and we have a cooler component of 0.1 kV. But when we check the statistic, whether this model actually improve the fitting from the 1 temperature, the end result is that the 2 temperature fitting do not really improve the overall fitting. But obviously, if we have more counts, more statistics, maybe this is something can be done more robustly.
Or an XIFU spectrum.
Yeah, exactly.
Okay, are there any more questions from the audience? I don't see anything in the chat, and I don't see any hands raised. Going once, going twice. If not, thank you again, Angie. Again, everybody said the talk was excellent. We completely agree that. Thank you for joining us today.